Welcome back to Talk Tensors. Ready for another deep dive?
Always.
Awesome. Today we're looking at investigating map-based path loss models, a study of feature representations in convolutional neural networks.
What a title.
Yeah, it is a bit of a mouthful, but it's all about predicting how strong a wireless signal will be as it travels from point A to point B.
Exactly. That's path loss prediction, and it's super important for planning wireless networks, whether it's for your Wi-Fi at home or cellular networks across the city.
And this paper uses machine learning and maps to get even more accurate predictions.
It's pretty cool stuff, actually. They're using CNN's convolutional neural networks to make those predictions, like teaching a computer to see how the landscape affects your signal.
Okay, so we're using maps and machine learning to figure out how signals lose strength. But there are a lot of papers out there. Why is this one so important?
Well, this paper goes beyond just using CNNs. It really digs into how we feed the information into these CNNs.
So it's like fine-tuning the recipe?
Yeah, you could say that. They're trying to figure out the absolute best way to represent different features, like the frequency of the signal and the distance between the transmitter and receiver, and then seeing how feeding those features into the CNN in different ways affects how accurate the predictions are.
So before we get into the specifics of what they did, can you give us a little background on this? How have researchers tackled path loss prediction in the past? What led up to this paper?
Sure. Traditionally, path loss models were based on complex mathematical equations.
Oh, I bet.
Yeah, they took into account things like the height of buildings, the types of terrain, and even the frequency of the signal.
So like a physics-based approach.
Exactly. And these models, they worked okay in some situations, but they often struggled to really capture the true complexity of the real world.
The real world is messy.
That's for sure. And that's where machine learning started to come in. In recent years, machine learning techniques like CNNs has shown a lot of promise for making these path loss predictions even more accurate.
Why are CNNs so well suited for this kind of task?
Well, CNNs are really good at analyzing images.
Right.
And in this case, we're using maps as our images.
Right.
So it's kind of like teaching a computer to see how the landscape affects signal strength.
So the CNNs are looking for patterns in those maps.
Exactly. So this paper builds upon that previous research using CNNs for path loss prediction, and it digs deeper into optimizing those input features.
Okay, so CNNs are our tool of choice here.
Yeah.
But what exactly did these researchers do differently to try to improve how we use them for path loss prediction?
Well, they focused on 3 different channel configurations. Each one represents a different way to feed information into the CNN.
Okay.
So the first one they call the original configuration uses a 2D grid to represent the distance between the transmitter and the receiver.
Okay.
Each cell in that grid corresponds to a specific distance.
So kind of like a digital elevation map.
Yeah, exactly, but for signal strength. And then they also have a separate channel for the signal's frequency.
Gotcha. So that's the original. What's the next approach?
Okay, so the second approach is called FINE, which stands for Feature Integration for Nonlinear Extraction.
Okay, I like the name.
And FINE simplifies things a bit. It still uses a separate channel for the frequency, but instead of that complex 2D grid for distance, it uses a simpler 3D calculation.
So it's a more compact way of representing that distance information.
Right. They're basically trying to convey the same information, but in a more efficient way.
And the third approach.
Okay, so the third approach is called FLIPHO, short for Feature Layer Integration in Perceptron.
Another kitschy name.
Yeah, right. And FB goes in a totally different direction. Instead of creating separate channels for the frequency and distance, they actually feed those values directly into the final layers of the CNN.
So they're just single numbers fed right into the end.
Exactly. They call those scalar features.
So it sounds like they're really experimenting with where in the process you feed that information to see how it affects those final predictions.
Yeah, that's a great way to put it.
So what kind of data did they use to test all these different approaches?
Well, to really put these configurations to the test, they used a data set of wireless signal measurements
Okay.
from 6 cities in the United Kingdom.
UK. Why the UK?
Well, each city had its own unique urban landscape. Different building heights, different street layouts, all kinds of different vegetation densities.
For a lot of variations to challenge the models.
Exactly. It was the perfect testing ground for these path loss models.
So it's like they chose 6 very different obstacle courses for their models to navigate.
Perfect analogy. So to evaluate which configuration performed the best, they used a technique called cross-validation.
Cross-validation. Can you explain that for our listeners who might not be familiar?
Sure. So they trained each model on data from 5 of the cities. and then tested it on that sixth city data that the model had never seen before.
A true test then.
Exactly. This way, they could really see how well each model could generalize its knowledge to new and unfamiliar environments.
So it's a real test of its adaptability. Which configuration came out on top? Were there any surprises?
Well, the results were actually quite interesting. Fine with that simplified 3D distance representation performed really well in some cities, like Merthyr Tydfil, Southampton, and Stevenage.
So fine is a bit of a specialist, thrives in certain conditions.
Yeah, I think that's a good way to put it. Because while it excelled in those cities, it had a much higher average error rate in the other UK cities. So that suggests that maybe simplifying the distance calculations might not be a one-size-fits-all solution.
Interesting. So what about flip? Did feeding that frequency and distance directly into those later layers actually work?
Sadly, no. Flip really struggled during both training and testing. While it showed some initial promise during training, its performance on the unseen test data was consistently worse than both the original and fine configurations.
Oh, wow. So skipping that step in the recipe kind of backfired.
Yeah, you could say that. The researchers think that feeding the frequency information directly into those later layers might have actually interfered with the CNN's ability to extract meaningful spatial information from the maps.
That's interesting. So it messed with its ability to see.
Yeah, you could say that. Remember, the frequency of a signal affects how it interacts with obstacles. So by introducing that information later in the process, they might have disrupted the CNN's understanding of how the landscape shapes signal propagation.
I see. It's like trying to teach someone to navigate a city, but only telling them about the traffic conditions after they've already planned their route.
That's a great way to put it. The timing of information is crucial for effective learning, both for humans and for these machine learning models.
So why did using that 2D grid for the distance seem to work better than just feeding in a single distance value later on?
Well, the researchers think that providing that distance information as a 2D grid early on actually helps the CNN grasp the relative sizes of the obstacles in the map.
Because everything on the map is to scale, right?
Right. They were working with maps that were all resized to the same dimensions, so having that spatial layout of distances likely helped the CNN understand how large those buildings or hills actually were in the real world.
So it gives the CNN a sense of scale. Yeah. Like a miniature model of a city versus the actual sprawling metropolis.
I like that. A perfect analogy. But those UK tests were really just the first step. The researchers really wanted to see how these models would perform when they were faced with a completely different data set, a different landscape, a different set of challenges.
So they went international.
They did. They set their sights on Canada.
From the rolling hills of the UK to the vast expanses of Canada. Why such a big change in location?
Well, it's all about testing the model's generalization abilities. Could these models trained on UK cities accurately predict path loss in a totally different environment? That's the ultimate test, right?
Mm-hmm.
Testing their robustness and how well they can be applied to different places. Yeah, they got a data set that covered a wide range of different environments across Canada.
Oh, cool.
Bustling city centers, those sprawling suburban neighborhoods, and even some remote rural areas.
So they really put those models through their paces. Did they make any tweaks to the models before they set them loose on all that Canadian data?
Yeah, they did. They retrained all three models, the original Fine and even Flip, using all 6 of the UK cities this time.
So no more holding out data for testing.
Nope. They wanted to give those models as much training data as possible before hitting them with the Canadian challenge. And they also decided to create something called ensemble models.
Ensemble models, what are those?
So ensemble models combine the predictions of multiple trained models.
So it's like a team of experts working together.
Exactly, like getting a second or third or even a 10th opinion. By combining the insights of multiple models, you can often boost the overall accuracy and make the predictions even more reliable.
That makes sense. So we've got our super trained models, our diverse Canadian data set, and now this ensemble approach. Time for the final showdown. What happened when they unleashed these models on Canada?
The results were pretty eye-opening. First off, all 3 models, even FLAP, benefited from having more training data and from that ensemble modeling. Their error rates on the Canadian data were generally lower than what they'd seen in those UK cross-validation tests.
So more data and teamwork equals better predictions.
Right. But I know you're still curious about Flip.
I am. It had a rough time in the UK. Did it redeem itself in Canada?
Well, this is where it gets really interesting. While Flip still struggled overall in Canada, it actually performed surprisingly well in a few specific cities.
Oh, wow. Flute paid the comeback kid.
Yeah.
What was it about those particular cities that made FLIT shine?
It seems like certain characteristics of those cities played a big role. They found that FLIT tended to do well in cities that had a lower proportion of what we call line of sight links.
Line of sight.
So that means where the transmitter and receiver have a clear path between them.
Oh, okay. So lots of obstacles.
Yeah. But they also had relatively low clutter density. So, like, not a ton of buildings or trees packed really tightly together.
So it's not just the model itself, but the type of environment it's being applied to that matters. Like the right tool for the right job.
Exactly. Maybe FLIT isn't a universal solution, but it definitely has its niche.
Right. So this unexpected success of FIP in those specific environments, that kind of opens up some new avenues for research, right?
Absolutely. It shows just how important it is to understand not only how to build these accurate path loss models, but also how those models actually interact with the specific environments that they're being used in.
That's a great point. And this leads us perfectly into our novel notion segment, where we go beyond the paper and think about some cool out-of-the-box research ideas. What if we took these CNN path loss models and used them to predict signal strength at like a super granular level? Imagine being able to predict path loss within a single building or even a room.
And hyperlocal path loss prediction.
Right. And the possibilities are endless.
Imagine optimizing Wi-Fi placement in your home so you don't have those dead zones anymore.
Ooh, that would be nice.
Or designing smart buildings that can adjust to signal strength changes in real time.
We could even have personalized wireless power delivery based on exactly where you are in a room.
Yeah, exactly. No more fighting over who gets to sit closest to the router.
But of course, there would be challenges to figure out. Right.
And of course, first we'd need super detailed 3D maps of indoor environments.
Yeah, because those CNNs need that visual data.
Exactly. And we'd have to take into account all the dynamic changes that happen inside buildings, people moving around furniture, being rearranged, all that stuff.
It's a lot more complex than a static outdoor environment. And what about privacy concerns?
Oh, that's huge. We'd have to make sure that people's privacy is protected while still enabling these kinds of cool applications. But as we've seen with FLIP, sometimes the most unexpected findings can lead to the most exciting breakthroughs.
Exactly. So maybe hyperlocal path loss prediction is the next big thing in wireless communication.
It could be.
Well, that wraps up another fascinating deep dive here on Talk Tensors. Thank you for taking us through this paper.
It was my pleasure.
This was a great exploration of path loss prediction and all the amazing things we can do with machine learning. I hope our listeners are as intrigued by this as we are.
Me too.
But before we sign off, I want to leave everyone with a final thought. What other factors beyond maps and distance could we use to make those path loss predictions even more accurate and even more personalized?
Ooh, that's a great question.
The possibilities are truly endless. Until next time, keep exploring and stay curious.